Now we're going to look at the atoms and molecules and how they are arranged. So crystalline solids have this regular repeating pattern, and it's called a crystalline lattice. You think of a garden lattice, it's, white cross pieces that something can grow up kind of like a trellis, right? But this is going to be three-dimensional. And the particles are going to arrange themselves in a way to minimize their energy, because that's what nature is always doing. And what we're going to look at is a unit cell. So that's the smallest unit of a crystal that, if you repeat it in 3 dimensions, gives you the entire crystal lattice. So here we have a 2-dimensional lattice where the lattice points are represented by circles. Those would be the atoms. And so here in pink, this is the unit cell. That is the smallest piece that, if you repeat it over and over again, you get the overall crystal. So you could think of that as being a tile on a tiled floor, right? And if you had identical tiles like this and you put them next to each other, you can see how that could happen. Oops. So another one could go there, and there, and there. You get the idea? There are lots of different unit cells. And these are some of them. Some of them have funny angles and correspondingly funny names. The ones we're going to look at are cubic unit cells. So this is a cubic unit cell, and it is the shape of a cube, right? So we have right angles, 90-degree angles, and all the edge lengths are the same. So these other things are also possible, but we're not going to worry about those. So we're going to look at some different unit cells, and it can be a little bit difficult to visualize what's going on, because it's hard to represent something three-dimensional on a two-dimensional screen. So in this section, all the unit cells we're looking at, the individual atoms are identical, even though they may have different colors in the illustration, but they're identical. The different colors are just so we can see it a little better. So a coordination number is the number of atoms with which each atom is in direct contact. So the atoms would be directly touching each other. They can strongly interact. And then packing efficiency represents the percentage of the volume of that cell that's actually occupied by the atoms, by the spheres. So high packing efficiency means there's little empty space. So if you have a high coordination number, you'll typically have a greater packing efficiency. Okay, so this is the 3 cubic unit cells we're going to look at. Simple, body-centered, and face-centered. And this is just a summary of all the information. You do not need to memorize that. So let's start with the simple one, right? So simple cubic unit cell has 1 atom at each corner. So this is like that square we were drawing on the 2-dimensional one, except this goes in 3 dimensions, right? So if we take another cube and stick it over here, right, then we'll have another piece of this atom. At each corner, we don't have a full atom, we have part of an atom. Right? This is 1/8 of an atom. So each corner is 1/8 of an atom, and there's 8 corners. So if you took all the pieces in that unit cell and put them together, you could make 1 atom. We can determine the length of an edge because it is twice the radius of the atom. You see that? So this is the radius of the atom, then the length of that side must be 2 times that, because they're actually touching each other. Any questions? So this is the illustration we were just looking at. And this is what it would look like if we showed the complete atom that's at each corner. And over here, what we're looking at, here's the unit cell. We're looking at this one in the corner. How many neighbors is it touching? So it's touching a neighbor here, and up there, and over here, and over here, and over here, and down there. So it's touching 6 neighbors. So the coordination number is 6. The packing efficiency is 52%. And you can calculate that by calculating the volume of one atom, which is how much is in here, and dividing by the volume of the unit cell itself, times 100. So it's 52% atom and 48% empty space. So let's do that on a 2-dimensional lattice. Calculate the packing efficiency of the 2-dimensional lattice shown here. So packing efficiency is, well, here it would be area of sphere or circles. That's the part we're interested, divided by total area of the cell times 100. So if we look at this white unit cell here, how many atoms, I'm sorry, they're not atoms, they're circles. How many circles are in that white box? A total of 1, right? Because here's a fourth of a circle, and there's a fourth, and here's a fourth, and another fourth. So if you take those pieces, you could put them together and make one circle. So the cell has 1 circle in it. So there's 1 circle per cell. Well, what's the area of 1 circle? Pi r squared. So 1 circle would be pi times r squared. Now we don't know what r is, but that's okay. What is the area of this square? Yeah, so each side, this is r and r. So the side length is 2r, and area is equal to length times width. So 2r squared, or 4r squared. So this is the area of the circles that are within that cell. The total area of the cell is 4 pi r squared. And then multiply by 100 to get a percentage. We still don't know what r is, but look, it cancels out. So the r squareds cancel out, and we're left with pi divided by 4 times 100. Calculator is in that stupid math print thing where it shows me 0.25 pi. That's not what I want. Okay, let me try that again. Pi divided by 4. Okay. And then times 100. So 78, I'll just do 3 sig figs, 78.5%. Technically, that would be an exact number because pi is essentially an exact number, and 4 would be an exact number. Any questions? They do a lot of fruit packing in Reedley, and most of the fruit is roughly spherical. And so this idea of packing efficiency is important if you're shipping fruit, right? You want to get as much fruit as possible into the box so that you don't have so many boxes and so much space taken up. But then you also have to consider how to keep the fruit safe Turns out this type of a structure is not the best way to get a lot of things into the space. Body-centered cubic, as the name suggests, has one atom at the center. So there's one atom at the center. That's the gold one. Different colors so we can see it better. And then it has atoms at each corner. Again, when we cut up the cell, each of these is an eighth of an atom, right? So an eighth of an atom from the purple adds up to one atom, plus the one in the middle gives us two atoms in the unit cell. Here's the derivation for the edge length in terms of R. You don't need to memorize that. If you need this equation on the exam, it'll be on the information sheet. You would need to be able to recognize this as a body-centered as opposed to a simple cubic cell. So this edge length here is equal to 4 times the radius divided by the square root of 3. It's more complicated because we can't just look at 2R because there's a gap here. Where they're touching is actually from corner to the opposite corner, and so you get into the Pythagorean theorem there. So this is body-centered cubic unit cell. Here it is if we show full atoms in all the positions. So we see that yellow one is nestled into the divot that's formed by that bottom layer of purple balls. And if we go over here and are looking at how many atoms is that one touching, this is hard to see, but it's touching 8. That's touching 8, so coordination number is 8. Packing efficiency here is 68%. An atom has a radius of 138 picometers and crystallizes in the body-centered cubic unit cell. What is the volume of the unit cell in cubic centimeters? Well, not that. What we need is this equation down here. So L, the length is equal to 4R divided by the square root of 3. So if this is our unit cell, and the edge length, right? This is asking for the volume. How do you calculate the volume of a cube? It's the edge length cubed. It's length times width times height, so L cubed. So we're going to take the equation for the edge length and cube that. So 4R over the square root of 3, that whole thing cubed, and that will equal the volume. So it's telling us the radius. So R is equal to 138 picometers. Now we can make things a little easier for ourselves if we think ahead. It wants the volume in cubic centimeters, right? So we can convert picometers to centimeters, or we can wait till the end and convert cubic picometers to cubic centimeters, which doesn't sound like a good idea to me. So this is the fast way to convert this one. So what does pico stand for? 10 to the minus 12. So instead of pico, I'm going to write times 10 to the minus 12 meters. So I just converted picometers into meters. Now I'm going to convert to centimeters. So I want meters on the bottom and centimeters on the top. So my meters will cancel out. And what does centi represent? 10 to the minus 2. So 10 to the minus 2 down there. 1 centimeter is 1 times 10 to the minus 2 meters. And, technically you can do this in your head, but it can get confusing because it's not 1.38, it's 138. So this gives me 1.3, that's not enough room there. 1.38 times 10 to the negative 8th centimeters. So that's the only variable here. I'm going to plug that into this equation. 4 times 1.38 times 10 to the minus 8th centimeters divided by the square root of 3 and cube the whole thing. So exactly how you do this on your calculator will depend on what calculator you have. So on the 36X Pro, I can press the, I have an X to the box button, which will raise whatever I have in the display to whatever power I tell it. So I'm going to calculate the value inside. 4 times 1.38 EE minus 8. And divide that by the square root of 3. So that's 3.18697 times 10 to the minus 8 centimeters. And then I'm going to press that X to the box button and 3 and enter. And so it will be this amount cubed. So 3.24 times 10 to the minus 23rd cubic centimeters would be the volume. Any questions? The third type of cubic unit cell we're going to look at is called a face-centered. And so here there is an atom centered on the face of this cube. So each face has an atom centered on it. So this gold piece here is half of an atom. And this is half an atom. And there's half an atom. And back there, and back there, and down here. So that's 4 atoms that are in half, right? So a total of 2 atoms. 1, 2, 3, 4, 5, 6. Sorry. I knew that wasn't sounding right. So I have 6 half atoms. And then what do the purple ones at the corner add up to? 1. So this is going to give me 4 atoms in total. And it'd be cool if we had an actual model of this that we could take apart and then you could put the pieces together and show yourself that yes, it is 4 atoms. Here they're touching along the diagonal face instead of from one corner of the cube to the opposite corner. So the math isn't quite as crazy, but bottom line is this guy down here. And I found that students misinterpret that sometimes. The R is not under the square root. So it might be better to write it as 2R times the square root of 2. Coordination number here is higher, it's 12. Packing efficiency is higher also, 74%. And here's the calculation of how many atoms are in the unit cell. And you can see now, looking at this, it's kind of looking like a blob, isn't it? Yeah.
Are we need to remember how in the corner each atom's an 8, and I guess how in the middle each atom's a half?
Yes, that is something that you should be able to figure out. Because I have seen ACS exam questions where they'll give you a picture of a lattice and say this is a simple cubic lattice. How many of this ion and how many of this ion are in a unit cell? So the eighth at the corner business, I think, is the hardest one to see. But think about, how would I complete this guy, right? I'd have to put a block in front, and then a block under the one in front, and a block under the one in back, and one to the side, and under that, and then one kitty corner out here, and under that. And so that I would need 7 additional cubes around this to make a full sphere here. Does that make sense? Yes.
My question is how do we, if we have a random thing like that one, how do we know if it's gonna, it's confusing when you think about this one, the face centered and the body centered.
So there would never be a situation where they show you this picture and say, what is it? Because that's too hard to see. Now, they could show you something that's more of an outline. Let's see if I can draw it. What kind of a cubic unit cell is that? Oh, wait. See, it gets really hard to draw. I want to show that there's this guy in the back in the corner, but there's also one in the middle. So fortunately, the names help a lot, because it's in the center, the body of the body, right? On this one, the center of an atom is on the face. And the one with just at the corners is simple. We can also do problems like this, but I'm not going to do this one. We can calculate the density of a substance using crystal structure information. So here, if we know the radius of a chromium atom and the type of unit cell, you can figure out, well, how many atoms are in one unit cell? Well, body-centered cubic, there's 2 atoms, right? One comprised of all the pieces at the corner and one in the middle. And so you can find the mass of 2 atoms, right? And then you can use the equation for the edge length. We have the radius. You can calculate the volume of the cube. And so you can take the mass of the 2 atoms and divide by the volume in cubic centimeters and get the density. So this is a more reasonable question. How many atoms are in the unit cell in the face-centered cubic structure? Four. So the face-centered, again, you have a cube. The ones at the corners, and there's always going to be atoms at the corners. That's one atom. And then each face of the cube, how many faces does a cube have? How many flat sides? 6. Like dice, right? They're actually numbered 1 through 6, right? So it's got 6 sides, and on each of those sides, those faces, there's half of an atom, right? So those would make up 3 atoms, plus the one at the corners is 4 atoms. We can also look at crystal structure as layers. So this is a simple cubic. So we have the corners at the centers of each atom. This guy is that guy right there. And there's nobody in the middle. So we can think of this as layers. How do you get that cell? Well, here's the layers stacked. A bottom layer, right? And then the next layer, this atom is directly on top of this atom. And this one is directly on top. Now, if you have some marbles or something around at home, you can try making this like in the corner of a box or something. It's not easy because they don't want to do this. This one wants to fall down into that little divot between the lower ones. So this is not a very efficient way of packing. It's a lot of empty space. It's more efficient when you're packing them to offset the rows. So here we have a row. You just can't get any closer than that. But the next row, instead of having them like this, we're going to shift them up half an atom because now they can nestle together a little bit closer, right? So we've offset one row by half an atom. So that makes the packing better in the layers. And then when we put the layers together, there's different ways to put the layers together. So we can take layer A and layer B, and we're not going to put layer B directly on top. We're going to put it in those little divots, the indentation. So between 3 atoms, there's a little indentation or divot here, right? And so this atom would like to sit down in that little hole, right? So we've got this second layer is offset as well. So we call the red one layer A and layer B, and so we can talk about a pattern of A, B, A, B. So there's 2 types of closest packed structures. They have the same packing efficiency, they have the same coordination number. It's just looking at the third layer that's different. So in hexagonal closest packed, this is not cubic. This is not a cubic unit cell. Here we have layer A and then layer B, and layer A is exactly lined up with layer A. The third layer and the first layer are exactly on top of each other, and these guys are sitting in the little holes in between. So this has a hexagonal unit cell. And so if you cut it up and look at the unit cell, that would be this guy. And we thought the cubic ones were hard. Ah! And this is just the beginning. But we're not going to go much further. Yes?
So when you're doing the coordination number, off of which atom is it based off of?
You can look at any atom, how many other atoms are touching it.
It's like, this one says 12, but I don't see how it does 12.
It's really hard to look at. Yeah. I would not try to count those.
Use my mark.
I don't think it'll come out asking you.
Did you count the simple cubic one? Or no?
You can count the simple cubic one. again, it's that piece at the corner. How many other pieces is it touching? It's touching 8. Up, down, back, forth, right, left.
Oh, you count all of them? That's
Mhm.
like you?
All of the ones that are touching an atom. So in this one, this red atom is touching this blue one, and that blue one, and this blue one, and that blue one. That's fairly easy to see. It's hard to see what it's actually touching on the inside. So we're not going to worry too much about this. But this is the unit cell, and it doesn't have 90-degree angles, so it's not a cubic. But there is a cubic closest packed. So here, layer A and layer B again, but now layer C is offset from layer A. So it's an ABC pattern. And this is the same as the face-centered cubic unit cell. It sure doesn't look anything like it, does it? This is the book's attempt to show us how that works. So here's one layer, second layer is offset, third layer also offset, the fourth layer would be directly in line. So put those layers together and tip them on their side, and then get out your butcher knife and start cutting, or maybe a saw would be better, and you'll end up with this. And there we have an atom on the face of the cube. So that's a face-centered cubic cell.